What we are going to discuss basically are set theoretical versus categorical issues, and finally 3 axioms that were never formulated explicitly in this course. And well, that's all the plan, and we'll discuss the exam separately. So, as for the set theory and categories, I'd like to summarize the problem whether we really needed to extend the boundaries of set theory. Speaking more poetically, the Cantor's paradise. Cantor's paradise. It is the Hilbert expression that belonged to the beginning of 20th century. It was the period when not everybody admitted the set theory and its language. However, Hilbert claimed that at that time it was well, the best mathematical universe for the mathematics that was contemporary then. Now let's start our considerations with topology. So, using, of course, the notations that we introduced in this course. So the first step that could seem quite artificial, sorry, I prefer another font. So suppose we have an ordinary topological space. In our notation, it is an object of the very well known category that that is the model of everything we are discussing, and that the name that constitutes a half of the title of this course. Perhaps at this point, I'd like to make a step back and recall that Poincaré was the first who, in fact, introduced several functors, like the fundamental group, well, for which he used that, well, is defined on the category of pointed topological spaces in several attempts. He defined homologies simply that are functors on just topological spaces with the values in abelian groups. And we see that these concepts, in fact, do not fit into Cantor's paradise, because they are by no means mappings. The difference, the basic difference is in the law that forbids to identify the isomorphic objects. We should think about various topological spaces as not various but isomorphic topological spaces we should avoid the question of them being equal. So mathematics was ready to, in the beginning of 20th century, mathematics was ready to work with the concepts beyond the set theory. However, it was not really needed because, well, here in the domain, we worked just with topological spaces, sets with some additional structures. In the codomain, we worked with groups. And, one should just adjust the terminology to work with these object of different nature simultaneously. However, in our course, we used another trick that seems rather artificial. That is to, let's formulate it as a functor. So considering, well, this functor is naturally denoted as op, the first two letters of the open sets, and it associates to any topological space the quite definite small category. Sorry, I don't remember whether we worked with it, perhaps no. And let me remind you that it is the category of small categories. Of course, with the functors as morphisms here. And this functor associates to every topological space T. Sorry, I wanted to say something different, excuse me, please. So I wanted to discuss the category of partially ordered sets. trying to imitate the calligraphic point. It's not so good. It is really T, not Y. Set. Well, let's believe that it is calligraphic. It associates to a topological space T the partially ordered set that we denote op sub T, and by definition op, the set of open sets belongs to, is an element of subsets of T, with the morphisms being empty or one element. As I said, this construction is quite artificial, and of course we can live without it. The main advantage of it is that it gives a very compact definition of a presheaf from that is just the functor of so here we consider, this is what I wanted to say, that this construction or, well, one element, let me write it explicitly, or one element. Today we'll have a chance to discuss one element sets. It is quite a serious matter. So here we make a difference between the set of open sets and the corresponding small category. That's what I was going to say. So this is an object of the category cat. So now the main advantage is that whenever we want to define a presheaf, we just say that it is a functor, a co-functor of from this category of open sets, the inverse category, to whatever we like. Say category, well, the arbitrary one. The arbitrary one. Okay. Any questions about this reminding of what we have discussed before?
Do I understand correctly that this functor is contravariant?
Yes, I call it co-functor, and this I use it in a non-standard way. The minus around the circled minus here means that it turns the arrows. Yes, of course. Here is
and the first functor, which you call OP, is also contravariant, right?
The first functor, no, it is a true functor.
But as far as I understand, given a morphism of topological
so this
spaces,
morphism, okay, let's it will be shorter and clearer to recall the well, in fact, it depends on the direction that we like. So here the morphism in this category of open sets is between two open sets, and it is a one element set. If this is a notation for today, if U is a subset of V and empty otherwise. No.
but I still believe that if we have a map of topological spaces, then the induced map on the set of open subsets is in the opposite direction. So I think that this functor OP should be contravariant rather than.
So say it again, please, Sasha. You still think that this functor,
given a map of topological spaces,
small seems contravariant to you still?
because the pre-image of open is open, and we don't know anything about the image of an open subset.
Don't know anything about the image of.
I mean, given a map of topological spaces, there is a map on the sets of open subsets, but it is in the opposite direction, because we know that a pre-image of open is open.
Yes, perhaps you are right. You are right. Let me think for a while. So we should not think about two different spaces. Yes, but it seems to me that the being a subset of open sets and their pre-images are preserved by all the operations. Am I wrong? Well, it's not a matter for improvisation. Thank you for the question. I mean,
I think that everything is right, but just the function should be from the opposite category. I mean, it is
okay. Okay, I'll think about it. Thank you. Well, then let's move further. And there is, I wanted to say a few words about, well, saving information by this step. Information from T to the associated partially ordered set of T. There is a funny, just a bit of general topology. There is a funny concept. So T is sober. Let's reconstruct the notation of the functor. Sober whenever the opens of T can be restorable by op T. And it turns out a small theorem from general topology is that the soberness of a topological space is equivalent to the following statement: any f closed f, so such that T, its complement, is open. So whenever F is non-empty, and irreducible, in the sense that it is not a union of smaller closed subsets. Let me see, anything else? No. So then it follows that this set is one element. Only points are elements. Only points are irreducible among all the closed subsets of the topological space. Now we know that Zariski has introduced the corresponding topology, and Serre, the brilliant sheaf theory. Sheaves together with their cohomology. These results that occupied several decades in the middle of 20th century were directed as taking Zariski topology, though being an exotic one, belonging to quite an exotic class of topology, to take them quite seriously. They worked, and the definition of a sheaf was one of the most effective. But according to this terminology, as we know perfectly from algebraic geometry, could be called terribly drunk. Well, whenever the dimension is larger than 1. For example, the affine plane contains lots of irreducible closed subsets, and this is what it is interesting for, well, affine plane, or better maybe projective plane. So here's a sign that in some topological sense, Zariski topology is quite insufficient for constructing the cohomology theories that would satisfy the while conjectures. And so here we have to, we are really bound to go beyond the set theory. Any questions about that? About this? Okay.
Apparently, I misunderstand the definition of soberness that you wrote. It is written here that open T is restorable by itself. In what sense?
The topology of T, when T is sober, its topology can be restored by the partially ordered set of its opens.
Then I'm probably confused by your notations, because it's written here that open T is restorable by open T.
Oh yes, sorry. I should. Yes, of course. Thank you. It is not a question, but of course the correct expression is that T is as a topological space is restorable by open T. In other words, two topological spaces. Well, we are speaking about the soberness of just one, and it means that it is homeomorphic to any other as soon as the partially ordered sets of their opens are isomorphic as partially ordered sets. Yes, now I've corrected the mistake, and it has become self-consistent. Did it?
Yes, it did.
Okay, so we move further, and I recall the subject that we have already discussed. That is the category of the coverings of T. And I'll just repeat briefly the reasons for which we have to leave the set theoretical mathematics. Well, the naive concept seems quite sufficient. That is, maybe we write something like curve T belonging to sub T. Yes, that means that there are the it is an element of set. T is the union of, say, open sets. I'll write O in such a way that we don't mix it with 0 from this covering. Yes, the covering set simply O. I am just reproducing the most naive and standard definition of what the covering is. However, we have discussed at some point in this course that, for instance, Czech cohomology needs limits of coverings, well, finer and finer coverings. That cannot be defined in these naive, of course, it can be defined, but in order to guarantee the filter property needed for such limit, we have to identify lots of objects. And we found it much more categorical and natural to consider, well, let me tell the truth immediately, that what we needed was the category of indexes. Even if we born ourselves only with compact topological space and consider only finite coverings, even in this case, we need certain operations on the categories that I will remind. Unfortunately, at that point, I didn't do the proper thing that perhaps was mentioned only in the category of used in the fine moduli space. We need coverings not only of the whole topological space, but of every open sets, every open set there. So the trouble is that here we perhaps we go not just beyond the set theory, but beyond the traditional, the elementary category theory. I'll explain it why. And as I said, Grotendika seemed not to be interested in these foundations, and the first authors considering Grotendika topologies inherited this attitude. After that, some theories like Grothendieck universes, some rigorous mathematicians demanded Grothendieck universes, but I think it is my personal opinion is, yes, there are lots of them, that it is just not a useful idea. I mean that you have to introduce lots of objects and axioms, while Grothendieck's thinking was extremely clear, that we best know maybe by his activities in descent-en-Funk theory or Galois theory. It is not at all a Grothendieck style. I think that we better consider this theory as belonging to future mathematics, where the 2 categories and 3 categories are as natural as just categories. Now I'll explain what it is all about. The thing is, now we turn to the main objects of the axioms. Namely, for all, well, we duplicate the quantifier, open. Sorry, I have promised to write down the precise axioms of Grothendieck topologies finally, but I won't do it just because it is boring and needs some duplication of letters. Instead, I'll rewrite the obvious properties of the usual topological spaces, however, meaning that we work with the arbitrary topology. So now I just fix the main actor of the theory. So for every object of the category of T, we associate the category I say sub O. It means when we do the indexation of something by the objects of a category, we are very well beyond set theory. The usual indexes belong to sets, as numbers belong to set of natural number. So what we need is a subcategory of the of our dear category set, category of sets. Sorry, I didn't define the status of what I'm going to speak, what I'm speaking about today. It is just a result of some rethinking of the foundational papers about Grothendieck topologies. So we have a special set of indices. Now let's use the remaining part of this whiteboard just to fix the main the main assumption that all every such category is closed with respect to the direct products. That is why it is impossible just to fix some set, index set. There is no Cartesian product in any set. Cartesian product is defined only in the categories of sets. Now let's recall the convenient concept of the covering. I prefer to use a special whiteboard for it. So any questions about this whiteboard? Well, then save it and clear, and just remind. And now we really define something like a category. As far as I understand, being rigorous, we need to consider something like a 3 category. I've counted it approximately. Perhaps I should remember that 2 category is a thing when the set of morphisms are not anymore sets, but the categories themselves, and so on. So these constructions needs several steps above set theory. So we consider the categories of coverings of all the open sets. So let's recall ourselves that O itself is an object. In our model, it is just an open set, but we consider the category of open sets. So the coverings of O, by definition, are just the pairs. We define the categories duplicating the usual set theoretical characters, and these are the pairs. A set of indices, not a category, and the procedure that associates to a label an actual open set. This is what you will never find in the classical papers. And here I is an object of the category index category, and U is a mapping from I hope the distinction between 2 kinds of I's is clear enough to the opens. What is it? Well, now I use the standard topological notations. So to the opens, therefore they are just sets of O sub O such that, of course, such that O is the union of all these elements. The last part is, of course, quite traditional. Sorry, here as we have introduced before, we use the notations like in the sequences. So I is mapped, small I is mapped not to U of I, but to U sub I. So this is the definition of the category. Now, perhaps we should emphasize what Mumford is doing in one of the first pages. The main difference from usual topological space, differences from the category top. The purely categorical differences are first the morphisms, set of morphisms from U, V now are not just, these are not just empty or one element sets. I write it down symbolically in terms of cardinalities. Repeat, re, and the final object that is the topological space itself, not mandatory. In some cases, we have to introduce it, but from purely categorical point of view, we don't need it. So this is the main definition. Now we turn to three axioms of Grothendieck topology, so that I formulate in rather, I give them name, unlike say Artin or Mumford do, and I hope they are easy to memorize. So first it is one element. Axiom, and it reads as follows: one element. So now the important detail I have mentioned before. We can consider any one element set in the index as an index set of O. Now, why do I emphasize it? When counting objects, we think that all the one element sets are the same, like the same. And of course, they are all canonically isomorphic. More than that, we are working with subcategory of category of sets. Therefore, this is meaningful. This notation is meaningful, just to contain the only element. However, maybe we better said that the axiom is about any final object, and any should be understood in a strong categorical sense. The thing is that in category theory, we never identify objects. So we should understand that there are lots of one element index sets. Then we formulate the one element axiom in quite a natural way. That is, we recall our definition. That is, we consider the pair where the index set is the element, is this set containing only this star, and the mapping is the star without any braces, of course, that maps to the whole open set O. And this pair should belong as an object to the category of coverings of O. So this is trivial axioms. By the way, I don't know why it happens so that 3 is a very popular number about concerning the number of axioms of fundamental objects, and classical topological spaces and groups and ordered sets are all formulated in 3 axioms, and Grotendika topology definitely demands the same number of basic axiom. Well, perhaps I first draw something obvious. Whenever we have a set, say, covered by some, well, round sets, and every round set is covered by square sets, then the square sets cover the whole topological space. Now, to put it formally, let me see. Whenever we have the covering of U. Yes, it is exactly here when where I'm going to use the set theoretical version of the axiom, because the categorical one will duplicate the notations. It needs both the indexing mappings and sets. But again, the matter is quite simple. That is, if O is, say, the union of O sub I prime, where I belongs to the index set I, and for any, again, no, just any element of I, the corresponding O I prime is the union of O I J double prime J running over the fixed set. Now here is a small problem that would say that it would be more natural to replace this J by something like J depending the index set J depending on I. I would say that mathematically and from the point of view of the intuition related to this picture, that would be quite natural. And instead of the picture of Cartesian product, we would say something, we would have something like a fibration for over every I, the set J sub I. However, nobody is considering the structures like that. So frankly, I don't know whether is it done just for simplification or there is some reason. I believe that these indexing sets did not deserve the sufficient attention, and perhaps the foundations of the whole theory should be reconsidered. So it should imply that the whole O is, of course, the union over, am I going to get into trouble maybe? I hope that not. By I. Oh, I'll write it explicitly what is going to happen when we turn to the true category picture. So here the picture is like this, or what is drawn here. And on the next whiteboard, I'll explain what is the categorical sense of it, and it is just simply the union of double primed subsets. So all this indexation is boring enough and insufficient. I'll have to move to the next whiteboard and explain what is the true meaning of the analog of it. First of all, perhaps I did not emphasize enough that, well, O prime intersected with O prime prime is, of course, the product, the fiber product in the corresponding category. That we always assume. We assume that the basic category has products as well as all the categories of indices, as we said. And now the main operations on the coverings, let's write it explicitly. So suppose we have a pair I and U as well as J and V, and suppose both are in the coverings of T, then we define the covering where the set of indices is the Cartesian product of indices, and I don't know how to call it, labeling, perhaps labeling mapping in the topological sense, and how should we call it in the general sense. We should think about that. Anyhow, the mapping associates to every pair ij from the product U sub A. Well, let's write down just the fiber product with V sub J. And we demand that the whole thing belongs to, is a covering again. So, well, here everything is written down, and the second axiom can be reformulated. And now the last one is the axiom of distributivity. And perhaps I'll bound myself in writing down the classical topological analog of it. That is an obvious one. Well, some exercise to write it down categorically, and that means that we intersected with the union of u sub i's is isomorphic to, is it? Yes, it is canonically isomorphic, of course, to the union of, well, I have started. Let's write down the products instead of intersections, just to recall ourselves that there is something categorical in our considerations of V times U sub I over T. So I think that the main, so that's all. It is the third and the last axiom. I think that the second one, the composition one, is formulated somewhat unsatisfactory, but when I wrote it down in all the details, I became terribly bored. So perhaps it deserves further thinking and further classification. Maybe as a final foundational remark, I would say that in this approach, again, sorry, perhaps I have forgotten to say that I believe that in future mathematics, nobody is going to be afraid of 2 categories, 3 categories, and so on. And in fact, I have participated in the conferences where young mathematicians were quite fluent in infinity categories. Though to me, a person, a mathematician from 20th century, it seemed well, not very well founded. However, I believe that there were times when the quantities, when the lengths were measured only in terms of elementary lengths. Therefore, the numbers, the true numbers, were only natural numbers and so on. But the concepts tend to develop, and of course, this the theory of Grothendieck topology belongs to this mathematics, this future mathematics. However, it really needs the some reformulation. I believe that today's lecture is not quite void because it fixes, I would say, 2 things: the number of basic axioms, just following exactly the first texts in Grothendieck topology that are Artin and Mumford text. And then clarifying the point that the main foundational issue is something like labeling the open sets. I don't know whether it belongs rather to mathematics or to the problem of language of mathematics, but it should, well, I'm going to think over it further and invite anybody related to this course to do the same. And I believe that the restriction of the labeling sets, the indices to be sets themselves, is unnatural. Perhaps the opens of the true Grothendieck topology theory belong to something more general and more natural. So I close here now. I think finally, any questions about today's material? Sasha, for some time I saw a green rectangle instead of you. Are you still here?
Yes, I'm here and I'm trying to fix this problem.
Okay. Well, we are quite close to the end. So if there is a true problem and if you have no questions, we turn to the exam issues.
Yes, I don't have any questions.
Okay, so we save this one and clear it. And well, the exam, whoever is going to pass it, is quite simple. So, well, conventionally, it is something like theory and something like practice. So, well, in theory, please fill in any, well, left to the reader. So your problem is solved. Left to the reader. So I mean, as basic texts, I mean the first ones, that is by Mumford, Artin, or whatsoever. If you just Google the Grothendieck topology, you'll find the ocean of the literature. But it seems to me that the original papers, the history of which was like step by step after Grothendieck ideas, Grothendieck did not participate just because at that old years, like 60s or so on, he was hoping to write down the total element de géométrie algébrique that he has never completed, as we know. So these were the pieces covered by these very active mathematicians. And almost at any place, you will find something left to the reader. I'm afraid that this job is rather boring, as maybe all the foundational work, but somebody should do it one day. As I said, Grotendika hoped to try it. By the way, Grotendika never left anything to anybody. He was a person who, well, in his youth, rediscovered the integration instead of Lebesgue and proved all the small lemmas. Just in terms of this exam, it can be as short as you like. But it would be nice if it is really covered to all the details. And the second part, so to say, practical, is calculate something that happened in the course, and it was not much. And again, my recommendation is to follow Mumford, 2 papers of Mumford that were discussed during the case. Well, in fact, any cohomological calculations, I write the notation as for moduli spaces, but of course it is up to the listener to choose the model. Basically, that is the Picard, the most persuasive calculation is that of Picard. Then, and well, the only thing that was discussed was Picard and Mumford. H2. Here, yes, it is the same notation, or whatsoever. So here I mean Mumford, the paper that I followed in the corresponding lectures on the abelian quotients. Abelian quotients. Of modular groups. So it is the calculations where the Grothendieck topology participate in somewhat hidden way, just manifesting the proper attitude to modular space as a stack, as Grothendieck topology formed by the modular spaces with the level structures. So perhaps that's all. Every detail is on the choice of, is up to a person who is going to pass this exam. Any questions about that? So I can be communicated by Maple until, well, let's set the date like May May 30th in 2 weeks from now. Before that, I can be communicated by mail. And well, perhaps any exam contact should be fixed beforehand. So that's it. Any questions about that? Well, then.
Could you please comment on the second part of the exam, I mean, which concerns calculations? Am I supposed to find some explicit model of some moduli spaces for some genus G, and then calculate its cohomology group in some kind of explicit way, and then try?
What you are saying is an ideal solution, but I'm afraid that it is rather involved. So instead, honestly, my recommendation is to write it in the additional color, to take Mumford on the Picard groups and calculate the Picard of M1 being Z over 12. So as soon as you understand this 12, I'll be perfectly satisfied. But of course, there are other solutions as well. Depends on your desire.
Here M1 stands for the Mumford compactification, or it is just the
paper
yeah,
is on the Picard group of the modular problem.
No. I mean, do we consider here the compactification of the moduli space?
No. But
But I believe that the uncompactified modular space of genus 1 curves is just a fine line, no?
Please mark this font written by the M is what Mumford calls the moduli problem. Again, it is not the final terminology. I can try to quote the goal of this paper. He starts with various cohomological questions about moduli spaces, including the one that was answered a couple of decades further. That is the question of rationality of moduli space, or unirationality, by the way, solved by himself. And then in the introduction, he writes that, however, there is a much better object that for which the field of rational functions is defined, though it is not explicit in this paper. But the main thing is that the Picard is defined in the same way as we have discussed it in the lecture. The abstract Picard of the fine moduli space is just the way of assigning a one-dimensional space to every curve in the world in some consistent way. And then it turns out that so this M sub 1 is not an affine line. It is, or in other words, it is an affine line together with all its modular coverings.
Okay, thank you.
And then this is the final result of Mumford's paper. It stops there. So in fact, you read from it exactly what is needed for this final calculation. And he gives several ways, basically two ways, purely algebraic one and transcendental. And my advice is to consider both. So in some sense, it just means reading this foundational paper. Okay.
Okay, thank you.